Okay, before I start on the notes, I want to show you guys a question that I would have asked you last year on one of your tests. This actually was apparently quiz 1. I just want to solve a question that we did last year, but we would have done this in degrees. My goal today is to help us do it in radians. So I hope this is familiar. If I give you the point 5, -8, and I ask you to sketch that, you might then say, well, 5, -8 would be right about here. So, you guys remember that? Yeah. And you draw like an arm that goes towards it right here, and you draw like say a triangle out of this, because this length is 5 and this is -8. What we could do for answering B then, to determine the distance from the origin to point P, is we could find this distance. How?
Yeah, you do like Pythagoras theorem.
Good, Pythagorean theorem, yeah. So you go 5 squared, it's 5, plus 8 squared, I'll ignore it's negative because that doesn't really make a difference. Square root them, so 25 plus 64. This is the square root of 89. Does that make sense? Remember doing that? Another thing I would have asked you to do then is calculate the primary trigonometric ratios. So that would be like something like, say, sine. Sine of theta is normally equal to the opposite over the hypotenuse. Well, this is the angle we're referring to right here. So the opposite would be -8, and the hypotenuse would be root 89. Remember that? Yeah. And then you do cosine of theta, and that's the adjacent over the hypotenuse. And you do tan of theta, which is the opposite over the adjacent. You guys are probably doing that? One of the things I made you do last year that actually wasn't a grade 11 curriculum, but I wanted to do it for this moment, was I taught you guys the reciprocal trig ratios. Do you guys have any recollection of what those are?
Oh, yeah, those are like weird ratios.
I don't know what they're called, I
Remember them. Okay, well, I'll start writing them out here. Sine has an opposite called cosecant, and it's CSC. And basically all you do is you flip whatever the sine numbers are upside down. So you do root 89 and you divide by -8. And then cosine has a reciprocal which is called secant. And same thing, just flip it upside down, so make it 89 over 5. And tan has a reciprocal called cotan. And that would be 5 over -8. And basically these are the 6 ways that you can write any two sides on top of each other. So it could be like A over B, B over C, A over C, or you can flip them all upside down the other way too. These are the only 6 possibilities we have. You guys recall doing that? Okay. The last step is the one I want to focus on today. We want to calculate the reference angle. We have a way of calculating this angle right here. But our goal now is to be able to do it in radians and degrees, not just in degrees. So one of the ways that we can calculate an angle, would be to go, first go to mode in your calculator, and let's do it in degrees first, just because that's what you guys have done in the past. If I tell you that sine of theta equals -8 over 89, if you go inverse sine, -8 over root 89, what this does is this should calculate an angle for you. Hopefully what I drilled into your heads last year, though, is that it's going to calculate an angle for you. We need to make sure that we use common sense, though, as to whether it's the right angle. It just said it was -58 degrees.
So that would be the...
Yeah, that means that like going backwards this way is 58 degrees. That's actually the reference angle. So how far is it the rest of the way around? Good. 360 subtract 58 is going to make it 302 degrees the rest of the way around. So you have to be very careful with your calculator, because your calculator is going to calculate an angle, one of the coterminal angles it's going to calculate, whichever one's the closest one. If you can kind of imagine that 0 is kind of the midpoint, if it tries to calculate the closest angle to 0, it either could go way in the future to 302, or it could go a little ways backwards to -58. So that's why it calculated -58. Now you didn't have to use sine though, you could have used cosine. You could have inversed cosine 5 divided by root 89. And it would give you positive 57.99. And again, you kind of have to use your discretion and say, well, there's no way that this angle all the way around here is positive 57.99. So again, what did your calculator do? Well, it calculated the reference angle instead. So just, again, it calculated this angle here being 58. Does that make sense? And you could do the exact same thing with tan. You could inverse tan -8/5. And again, it gives you a negative angle, basically referring to the fact that, yeah, this is going backwards. You guys recall doing that? All right, today we're going to do similar stuff, only we're going to do it in radians. So, okay, some review slides again, but we've already done a little bit of this. SOHCAHTOA, c² = a² + b². Do you guys remember these rules? Clearly, it seems. Here's a slide just talking about how we can plot a point on a grid. And if we plot a point on a grid, we can always make a triangle out of it, where you have an x-axis side, a y-axis side, and then a radius is what I'm going to refer to this from now on. Did I use that term last year with you guys, a radius idea? Or just hypotenuse? Okay, hypotenuse works, but does it make sense that if this is like inside a circle of some kind, that we could call it a radius as well? You could call it a hypotenuse, you can call it a radius. So this leads to kind of a new definition of SOHCAHTOA. You guys remember learning SOHCAHTOA is like sine is opposite over hypotenuse? Well, in a circle, what we've decided to do is we call it a unit circle. And that's our title of our notes today. In a unit circle, the radius is being defined as 1. Make sense? So this is a circle that, regardless of where I draw this line, if I draw it in any of the quadrants, this is a distance of 1. That's your hypotenuse, basically. Well, if it's a unit circle, then, really sine, you guys used to know sine is opposite over hypotenuse? Well, your opposite is now a y value, and your hypotenuse is now a radius. Sometimes we write it like this, though. Sine of theta just equals just y. I just told you the radius was equal to 1 in a unit circle. So if you're dividing by a radius of 1, do you even really need to divide by it? Say no. So sometimes we can say that sine of theta is actually equal to a y value. However tall this is, that's what sine is equal to now. Cosine is normally equal to adjacent over hypotenuse. So the adjacent would be your x value. Your hypotenuse would be 1 if it's a unit circle. So in that case right here, your cosine is just really equal to x. We can kind of ignore the radius. And then tan, unfortunately, tan doesn't involve radius. It does involve y over x, though, because that's opposite over adjacent. And so we have like new formulas, kind of. Like they're not entirely new because SOHCAHTOA still works. You just have to recognize that opposites and adjacents are now x's and y's. Now I should add this though. If it is a unit circle, the radius is 1. We don't always have to use a unit circle. It could be a radius of 5 or 7 or something like that too. So don't just assume that it's just y or x unless we know for sure that this radius is 1. So here's an example just pointing out that you can have negative values. Let's say that the unit circle, the triangles that you draw end up being in this quadrant right here. Your y value is positive, but your x value is negative. Does that make sense? And that could mean that when you do cosine or tan, you actually get negative numbers when you do like a cosine of like a larger value. Here's just a slide just showing kind of all of the different possible locations you could have angles. I just want to show you guys an acronym, a rule. Did I talk with you guys about the cast rule last year, or is that not something we covered? Did we talk about that? Okay, so let's review it then, if that's something you recognize that word. Cast refers to where cosine is positive, where all of them are positive, then where sine is positive, and then where tan is positive. And the way the cast rule works is you start here for C, there for A, there for S, and there for T. You actually start with it like one quadrant below. So let me see if I can show you this here. In this quadrant right here, are there any negative x or y values? Okay, that's why it's A. Everyone, all things are going to be positive. Does that make sense? And do the same thing in this quadrant here. So C, A, S, T. Is there a negative value in this one right here? What's negative, x or y? Okay, x is negative. So that means that cosine has x in its formula. It'll be negative. And tan has x in its formula. It'll be negative. So we put an S in this quadrant because sine is the only thing that doesn't involve S in its formula, and so sine will still be positive. So the CAST rule works, and it tells you which identity is positive. Does that make sense? Third quadrant. Who's negative in this quadrant? X and Y are actually both negative, which means that here you have a Y, so sine is negative, and here you have an X, so cosine is negative. Tan is different though. You have a negative X and a negative Y. Well, if they're both negative, it makes it positive. So that's why T goes in this quadrant, because tan is actually positive in the third quadrant. And then one more time. In this quadrant here, the thing that's negative is just Y. So that means tan will be negative and sine will be negative, but cosine does not involve Y in its formula, so it would remain positive. So that's why cosine goes here. Does that seem familiar? Here's just a picture just in pointing out that unit circle concept again here, where this is your X, that's your Y, and if it is a unit circle, your radius is 1. Sometimes I give you a question and it's not a unit circle, and we'll try to make it a unit circle, and we'll force the radius to become 1. I'll show you how to do that in a bit. Here's a slide showing you about that CAST rule I just showed you about. So, lots of pictures, I guess, to start. Another picture about the CAST rule. I don't know, cut it out and put it on your data sheet if you need it. So, okay, let's do an example. Let's actually try something now. So we're going to try to find all the primary and secondary ratios based on the point -3, -7. And then we're going to try to determine the value of theta. But I'm going to put a little note here. We're going to do it in radians. That's going to be our new twist. So where does -3, -7 go? Probably right about here, I'd say. That's -3, -7. How do I draw the reference angle triangle? Like this? No. Yeah, always draw it to the x-axis. We just, as mathematicians, had to choose one way to be the standard way, so they just chose x-axis. I mean, they could have chose y-axis, but it's been defined now as we're always going to the x-axis. So there we've made ourselves a triangle. There's a -3 right here. There's a -7 right here. We should be able to find the hypotenuse. (3 squared plus 7 squared) square root the answer. Actually, I want to leave it as a square root. I'm going to make this root 58. Anybody else get that? Okay. First thing here, is this a unit circle, technically, at this point? No. What does the radius have to be for it to be a unit circle? What is the radius currently? Root 58. Is that 1? No, it's not. So here's the first trick I want to show you. To make it a unit circle, what we're going to do is we're going to divide all values by whatever the radius is. Because if you do it equally to all values, that's kind of a fair mathematical thing to do. So I'm going to divide this by root 58. Because if I divide that by root 58, it's just going to be 1. I'm going to divide this by root 58. And I'm going to divide this by root 58. I'm going to redraw this triangle now a little bit clearer because it did get a little messy there. So here's my triangle. The radius now, the hypotenuse, root 58 divided by root 58. On purpose, we did this so that it would be 1. That makes sense. This value right here will now be whatever -3 divided by root 58 is. That's just a decimal number of some kind, right? And this value right here will be -7 over root 58. Again, that's just some decimal number. But now we've plotted this on what's considered to be a, I'm using my fingers, a unit circle. Does that make sense? I'm just going to erase my writing there. I want the room. Okay, what else did this ask us to do? It asked us to determine all the primary and secondary trig ratios. Let's try that. What is sine supposed to be equivalent to? Well, it's supposed to be y over r. Opposite over hypotenuse. Oh my god.
Oh my god.
That's awesome.
So everyone cleans up the chair.
Cleans up what?
Like, cleans up after the desk.
Oh yeah.
Okay.
I
Just wanted to know once to tell your class.
think so. I haven't really had a problem with it. Have there been problems with other classes and them not cleaning up? Well, make sure you like put a smack down on them, okay?
Okay. We'll just miss your class. So I'm pretty
Make sure you clean up. These guys are pretty good. Thanks, guys. Alright. Okay, sine was supposed to be y over r. But really, we can just make that whatever y is. Because my radius I made to be 1, right? So sine is going to be whatever y is. My y value looks like it's minus 7 over root 58. Whatever that number is, that's what it is equivalent to. What's cosine going to be equal to? Well, cosine is equal to x over r, but don't forget, we just made radius equal to 1 on purpose, so really it's just equal to x. And your x value is negative 3 over root 58. Here's the trickiest one. Tan. Tan is equivalent to whatever y is divided by whatever x is. So your y value is minus 7 over root 58. And that needs a big fraction because you divide that by your x value, which was minus 3 over root 58. There's something you can do here to clean this up a bit. Yeah, the root 58s can cancel, basically. You have a 7 and a number on the bottom of a fraction, and a 3 and a number on the bottom of a fraction. And the number on both bottoms is the same number, so you can cancel the root 58s. So you then have negative 7 over negative 3. Let's just call that 7 over 3. Which quadrant are we in? Well, the third is supposed to be the letter T. Is tan the only thing positive in that quadrant? Yeah. This one was negative, this one was negative. This one had a negative over a negative, but a negative over a negative makes it positive. Alright, so let's revisit the secondary trig ratios. Does anyone remember the opposite of sine? Good, it's cosecant. The way I remember this, myself, by the way, is that cosine has the word co in it. And so it does not need another co. So sine does not have the word co, so it needs to, its opposite needs a co, so it's cosecant for that one. So that'll be root 58 divided by minus 7. Whereas cosine already has the word co in its word, so it just needs to be a regular old secant, as opposed to the cosecant. So secant. And that's going to be root 58, and we'll divide by negative 3. And lastly, tan does not have co in its name, so we'll add a co and call it a cotan. And it would be 3 over 7 instead. All right, last step. We ultimately want to determine the value of pi, or the value of theta. We want to do it in radians. So one thing I need you guys to be fairly comfortable doing is, in your calculator, go to the mode, and let's work with radians instead. And before I do any work, I don't want to hazard a guess as to how many radians it is all the way around to here. Four is not a bad guess. There's 3 radians basically at the halfway point, right? Because there's this pi at the halfway point, 3.14 radians at the halfway point. So it looks like there's probably 4 point something radians. So now to use our calculator, though, we need to have good interpretation skills. I can use any one of these ratios here to solve for what theta is. I'm actually going to do all 3 of them. So I'm going to inverse sine the negative 7 divided by the root 58. That gives me negative 1.165. Okay, so So I need to be able to interpret what the heck that means. Your calculator found an answer, but it might not have found the answer we're looking for. Our estimation skills thought that we needed about 5 radians here, and it went backwards 1 radian. Well, negative 1 radian would probably put it into this quadrant here. That also is probably not correct. So what did it actually find? I believe what it did is this 1.165 radians. That's your reference angle. That's what it's calculated for you here. Does that make sense? I'm gonna try another one here. Let's inverse cosine the negative 3 divided by the root of 58. That gave us 1.956. Huh. That's even worse. That doesn't help either. Well, what's happened here is, you know, cosine? Cosine is allowed to be negative in a few different places. Cosine's allowed to be negative in this quadrant down here. But cosine's also allowed to be negative up in this top quadrant right here. That makes sense. And what your calculator did is it pretended there was a triangle right here, and it said, hey, look, I found a cosine triangle that is also negative. And it calculated the angle from here to there, which is not the angle we're looking for. That makes sense? For the first one, actually, I think what your calculator did here is you asked your calculator to find a negative value for sine. So your calculator said, okay, well, first quadrant, can sine be negative? It said, no, everything has to be positive. Then I went to the second quadrant. Can sine be negative? No, actually, it can't be there either. And then your calculator said, okay, I'm tired of going forward. Why don't I go backwards? So it went into this quadrant right here. Can sine be negative in this quadrant right here? Sure. And so what your calculator did is it went backwards. And it went backwards 1.165 radians. And it found an answer in this quadrant. Still not the one we're looking for, though. Let's do one more here. Let's inverse tan 7 over 3. That gave us 1.1659. So here's what your calculator did. It said, you want me to find you a spot where tan is positive. Is tan positive in the first quadrant? Yeah. So rather than finding you an angle down here in this third quadrant, it just drew a triangle very similar to it in the first quadrant and said, the angle right here is 1.165. That's perfect, yeah. So what we've now basically figured out is this angle right here, called the reference angle, it is 1.1659. And so like Brianna said, we need to add it not to 2 pi, but just to 1 pi. You said 1 pi, right? Okay. Yeah. So if all the way around from here to here is pi, add those together. So adding it to pi means that the actual answer is 4.307 radians. And now that actually kind of fits logical sense, because I think Brad was the first one to maybe point out that it should be 4-ish radians. That actually fits. One of the most frustrating things that you're going to find about doing trigonometry is your calculator is going to find you an answer. But it may find you an answer in a different quadrant than you're looking for. Because your calculator is going to find the first answer it can find. So if you want it to find a sine that is positive, it might find you an angle in this quadrant right here. But if you're looking for a sine that's positive, you might have actually been looking for one in this quadrant here. So you actually have to use a little reasoning skills and work backwards. For us, we were looking for a sine that was negative. So a sine that's negative could be down here, or a sine that's negative could be right here. That's why it gave us that negative answer to start with. Does that make sense? We'll try more examples, obviously. Yes?
You just use the first one that you had?
You don't actually have to use all 3.
Yeah, but like if you use the first one that you had and you changed it to a positive, you just added it too.
That's basically what we did. Yeah, we used the first one. This first one right here gave you a negative number. I just recognized, okay, what it actually gave me was a reference angle in this little corner here. So the angle out of the triangle that would have been here should be the same as the angle you'd get in this one here. So that's why we just added it to the pi.
How did you figure out how many radians it was?
Well, the final answer, we took the 1.159 and we added it to pi.
Oh.
Because the way the circle works is that this is pi right here, and this little bit is like 1.16 radians more than pi.
Okay, got it.
Okay. Okay. That's not a slide we need to talk about. How many more do I have here? Actually, this is probably a good stopping point. Let's do one more example here. Yeah, let's do one more example, then we'll take a break. Okay. So let's say that your calculator, not your calculator, let's say that you're told that cosine of theta equals negative 0.4. Why is this not a fraction? Isn't cosine always supposed to be like an adjacent over hypotenuse? The radius is 1. It's a unit circle, so the radius is 1. So really this negative 0.4 is actually the x value, because cosine is actually telling you what x values are. So based on that information here, what I need to do is I need to figure out which quadrant can cosine be negative in. Well, can cosine be negative in the first quadrant here? No, everyone's positive. Can cosine be negative in this quadrant here? Yep. So there could have been a triangle like this. That's a logical place. Or there could even be a triangle in this quadrant right here. Both of these two would involve a cosine that is somehow going to be negative. Why not in this one right here? Yeah, the x-axis is positive in this one right here. So sometimes because there's two different locations, I'm going to give you information like this that will help you narrow down which of those triangles you're actually looking for. If I'm telling you that you're looking from pi over 2 until pi, which quadrant is it? Sure, that'll work. Quadrant 2. Yeah, this is 1, 2, 3, and 4. We don't care about this one because this is where half of pi is, and this is where pi is.
So like you're giving us parameters.
That's a good way of putting it, yeah. So because there's more than one location where you could have a negative cosine, I'm giving you the parameters and telling you which of the triangles we actually care about. Okay, so here's a bit of an issue then. We want to try to find the other trig ratios. I can actually kind of plot some stuff on this circle here. Negative 0.4 is going to be right here. This is negative 0.4 right there. Do I know any numbers on this triangle though? Good, the hypotenuse is 1. Based on that, that's enough information to work backwards and solve for the y side. You just have to use Pythagoras' theorem correctly. Pythagoras' theorem is c squared equals a squared plus b squared. But we actually know the c squared, that's going to be 1 squared. Let's let your a squared be negative 0.4 squared. We actually have to solve for b squared. 1 squared is 1. 0.4 squared is 0.16. And that's equal to b squared. Well, no, you add that to get b squared. So how do you get b by itself? Subtract it to the other side and square root. So you need the square root of 0.84. So I'm going to round it to 2 decimal places. Let's call it 0.92. Anybody else get that? You guys got that? Yep. Okay. Is that going to be a positive or a negative? In this quadrant here, it would be positive. But hypothetically, let's say we're looking for this bottom triangle that I crossed out. You'd have to make it negative 0.92. I know that you calculated it using Pythagoras' theorem as positive 0.92, but you're always going to calculate a positive when you use Pythagoras' theorem. So if it's ever in like one of the lower quadrants, you might actually have to use like some common sense and say this number right here would have had to have been negative 0.92. But that doesn't matter because we're not using that quadrant anyways. So let's determine the value of the other 5 trig ratios then. So what is sine going to be? Well, sine is just the y value. So it'll just be 0.92. Technically, it's the y value divided by 1, but our radius is 1, so we're good. I'll just write it out again. What's cosine's value? Well, they told us it was negative 0.4. What will tan's value be? Sure, that'll work. So 0.92 divided by 0.4. I got 2.29 negative when I take these two numbers and divide them by each other. The other ones are a bit trickier. cosecant, there's actually a nifty little trick you can play. Rather than trying to rearrange things like this, have I shown you guys that like you can take 0.92 and press this -1 button? Ever shown you that button before? The -1 button basically means that you're making it into a reciprocal. You're flipping the fraction upside down. So it's going to be, that's right, 1.09. It's right below, right above the squared button. Basically what you're doing is you're taking 0.92. Oh, let me clear that. You're doing 1 divided by 0.92.
I don't let me lose it.
So you can do the same thing with the cosine one. You can just reciprocal it by taking -0.4. Reciprocal, so secant would actually be -2.5. And cotan, you can just take this guy right here and do the same thing. If I could go back up and find that number, I'd use the whole number, but I guess I'll just do this, 2.29. -0.44. Does that make sense? Yeah. Okay, one last thought, then we'll take a break here. I know it didn't ask for it, but let's say we wanted to try to find this angle right here. Estimate what that angle would be before you actually solve it. How many radians? How many radians? Did you say 130 degrees? It's not bad. Yeah, like 2 and a bit radians. Yeah, okay. So what I could do is I could second cosine -0.4. And this should give me, actually that's not bad. So let's consider what this did. Your calculator, you asked it to find a negative cosine value. Can your calculator find a negative cosine value in the first quadrant? No. So then it moves on to the second quadrant. Yeah, 1.89 radians, that makes sense. Let's say you did the inverse sine though of your 0.92. What you asked your calculator to do was find me a positive sine value, and it would start in quadrant 1. And in quadrant 1, you could do a positive sine value. And so what it actually calculated for you was this little reference angle right here of 1.16. Well, that would be this little angle right here of 1.16. I bet you if you added these two numbers together, what should it equal? Pi, yeah. Yeah, because basically that's what happened is we've actually calculated from here to here is about 1.98 radians. Your calculator thought this little bit right here was 1.16 radians. So if you put 1.16 there and added these two numbers together, 1.98, and this won't be perfect obviously, plus 1.16. Actually, that worked out pretty well actually. I couldn't ask for that to go better. Okay, why don't we take a break? When we come back, I got more. Sorry, it's a long day. It's a long week, actually. I apologize. It's the beginning of a unit. Okay, here's a diploma question on kind of the stuff we've just been talking about. So, you guys want to try this yourself, or should I walk you through it? Okay, it's too early. Okay, so here's a diploma question. Let me walk you through my thoughts as I read this. When you get a trig question, there's going to be lots of little bits of information, and you have to be able to interpret all the little bits in order to solve the puzzle. So like the very first thing I come across here is they tell you that cosine of theta is 4/5. So that is enough to actually start plotting on a grid two possible triangles. I'm going to plot them both now, but we're actually going to eliminate one in a second. If cosine is 4/5, that means cosine has to be a positive value. Where is cosine positive? Either in this first quadrant right here, or possibly in this quadrant right here. Those are the two possibilities. And if I labeled stuff out, cosine is equal to adjacent over hypotenuse. Is this actually a unit circle at this point? I guess not, because if the adjacent is 4 and the hypotenuse is 5, I guess it's not exactly a unit circle at this point. I could make it a unit circle if I kept dividing everything by 5. I mean, I could make this be 0.8, and that could be 1 if I wanted, but I'll just work with it as not a unit circle for now. Does anybody know what the other side is going to be just off the top of their head? Anybody ever heard of the 3, 4, 5 triangle? It's a very common triangle where if the hypotenuse is 5, the two sides are 3 and 4. If you haven't heard of that, the way you solve it is you go like 5 squared equals 4 squared plus a squared, and you work backwards and you solve for it. But I promise you get 3 if you do that. You see how I put 3 in both of these quadrants here, though? That's actually not right. One of them should not be 3. Good. That way, that guy should be negative 3. Okay, so I've now taken care of just purely this information here. So next step. As I keep reading, it's going to limit things for me. It's going to tell me we only care about the triangle between 3 pi over 2 and 2 pi. So top triangle and bottom triangle do we care about? The bottom one, yeah. Because this is where 1.5 pi is. This is where 2 pi is. This first triangle is not in the correct quadrant then.
Less than 2 pi.
The top quadrant is really between 0 and 0.5 pi in a way. So here's my last step. We want to figure out what cotan of theta is equal to. Well, what is the formula for cotan? If you don't have it memorized, it's the opposite of tan. So if tan is equal to, say, opposite over adjacent, then this guy is adjacent over opposite.
It's x over y.
That's another way of doing it. You could do your y over x and your x over y. Depends on if you have it memorized. So your adjacent, or your x value, is 4, and your opposite value, or your y value, is negative 3. So therefore the answer is D. Does that make sense?
Yeah.
Let's try another old diploma question. Too fast? Sorry. Alright, so here's another old diploma question. This one's similar in concept, but there's a twist to it. Now I'm going to tell you a point, but I don't even tell you a point technically. I tell you 8k and negative 6k, and then k is greater than 0. So I want to start with this. If k is greater than 0, what does that mean?
Yeah, it's like,
Well, it has to be positive. That's probably the best way of putting it, because it's not. It could still be a decimal number, but it's positive. What that means then is that this 8 is going to remain positive, and this negative 6 is going to remain negative. That's what this information here kind of tells you. So I'm going to plot the other parts of the information here. It says that this is on a standard position angle, so I'm going to start plotting. 8 would go right about here, and negative 6 would go maybe about there. This is 8k, whatever k is, and this is minus 6k, whatever that is. So I already know which quadrant this is in. This is in that fourth quadrant. Using my cast rule, C-A-S-T, I should be able to tell you the signs in this quadrant. Cosine should be positive, but sine and tan should both be negative. Based on that information, I might be able to narrow down the answers here. Because here it says, what are the values of sine, cosine, and tan? So as I look through here they want sine to be negative, that could work. Here they want cosine to be positive, that could work. And tan negative, that could work. Here's another negative, positive, negative one. I'm going to rule this one out though, because that one doesn't go negative, positive, negative. It has the wrong order to it. So that helps narrow it down a little bit. I want to plot some more here. This is 8k, and this is minus 6k. We should be able to solve for this side right here. I have to use Pythagoras' theorem though. So the way it would work is that 8k squared plus minus 6k squared, that's going to equal c squared. 8k squared is actually 64k squared. That'll be 36k squared. When I put them together, I'm going to get 100k squared. And when you square root it, you got to square root both. So the 100 square roots to become a 10, and the k squared square roots just become Maybe that even makes sense. You guys were talking about that 3, 4, 5 triangle just a second ago. This is just twice as big. Rather than 3, 4, 5, it's 6, 8, 10, which is everything doubled. So. Okay, well let's write out what it is. Sine is going to be your opposite over your hypotenuse, or if you prefer, your y value over your radius. What happens when you take minus 6k divided by 10k? Well, the k's cancel, and you get negative 3 over 5. And I think I'm already done then, because that's the only one that starts with negative 3 over 5. I mean, I can keep trying the other ones just to confirm, but I think that's, you guys can probably do that, right? Like cosine would be the adjacent over, so that'd be 4 over 5. So that fits. Does that make sense?
Yeah.
Awesome. Okay, more stuff. You know that 3, 4, 5 triangle I just showed you? That is actually one of the triangles that's very common, 3, 4, and 5. There are 2 other triangles that are so common that we use them so much that they're considered to be what's called exact value triangles. I'd like to show you these triangles now. So one of them is the 3, 4, 5 triangle, but there's 2 others I want to talk about. So one of them involves a 45-degree angle triangle. It's a right-angled isosceles triangle. I'm going to draw that here. If I draw a right-angled triangle, this is very, very bad. Right-angled triangle. And let's say I make these angles 45 degrees. Do you guys know a rule for isosceles triangles that says that whatever this 45 degree is, this side right here, and whatever this 45, this side right here, they have to be the same distance as each other? You guys ever heard that before? Okay, well I'm just going to choose a distance then. I'm going to choose that this is 1 and this is 1. I'm making up a number. 1 is a reasonable number because it's just a small whole number. Well, if these numbers here are chosen to be 1, it means this side right here is the square root of 2. The reason why it's the square root of 2 is that using Pythagoras' theorem, 1 squared plus 1 squared equals c squared. This is just 2. So when you square root it, this side right here is the square root of 2. And this is a very famous triangle then. Kind of like the 3, 4, 5 triangle. If you ever get a 1, 1 root 2 triangle, it actually involves 45-degree angles in the corner. The other famous triangle is an equilateral triangle. So all sides are the same. That means this side, and this side are the same. And it actually also implies what all of the angles are. They all have to be 60s. Because 60, 60, and 60 adds up to 180. Well, it's actually not this triangle we want to work with. What we want to do is we want to cut this triangle exactly in half. So imagine that it was an equilateral triangle, but now you actually have half of an equilateral triangle. What's happened then is this angle in the corner is still 60. Yeah, because you've cut it in half, so now this one's 30. And by default, the other angle has to be 90, because that's what it would have to add to. Okay. Now what we choose for this one is we choose to make this side right here 1. We have to arbitrarily assign a number to one side. Well, if this right here is 1, then wouldn't this half of the triangle over here also have been 1? So wouldn't the whole side length be 2? Well, that means that this right here is 2, or more importantly for us, this side right here is also 2. That tells us the other side. And then based on that, we can use Pythagoras' theorem and say that 2 squared is equal to 1 squared plus b squared. That's 4 equals 1 plus b squared. Long story short, b is equal to the square root of 3. And this is the other, what's considered to be a special triangle. What's useful about these triangles then is one of them tells you information about 30 degrees and 60 degrees, which are kind of nice round numbers. And the other one tells you information about 45 degrees, which is also kind of a nice round number. Write this down, maybe not right this minute, but throw it on your formula sheet, because we're going to use it considerably over the next little while. One more thought. I might have it on other slides here. Now that I actually talked about this a little bit, 45 degrees is actually in radians pi over 4. you can calculate that yourself, but it's pi over 4. So this triangle right here needs to have a 1 and a 1 and a square root of 2. That's how either a pi over 4 or a 45-degree triangle works. The way I remember this one myself is that 45 degrees and 4 both involve 4s. For the other triangle, where it goes 1, 2, square root of 3, for this one here, 30 degrees is pi over 6, and 60 degrees is pi over 3. So the way I recall that one is that the one with the 3 actually needs the 6 in the other unit, and the one with the 6 needs the 3 in the other unit.
Mr. Petluck, can you please call 100?
Based on these triangles, I'm going to show you how to solve some more problems. I'm going to skip through those picture slides. We'll just do this one here. I'm going to close that door. So my question is, let's find the exact trig ratio for sine of 7 pi over 4. So first thing you could do, if you wanted to, you could go to your calculator, and you could literally type in sine, sine of 7 pi over 4. And it gives you that. Here's the problem though. That's not considered to be an exact value. That's like a rounded decimal number, and we're not looking for that. So although you could do that, we're trying something else. 7 pi over 4 is an angle. Where would 7 pi over 4 be if I drew it out as an angle?
Be down with the lower quadrant.
This one right here, yeah. Because if I draw out quarters, this would be the first quarter, that would be the second quarter, the third quarter, the fourth quarter, where Tom Brady is very good, by the way, fifth quarter, come on, that was good, sixth quarter, seventh quarter.
Mr. Petluck, can you please call 100?
So all the way around to here is 7 pi over 4. Based on our knowledge then of how triangles are going to work here, according to the cast law, would we expect sine to be positive or negative? There's a C there. C means cosine is positive, and sine is negative. And if I kind of even draw a triangle out right here, this is going to have to be a positive value on this axis, but the one that sine matters is the y value. This will be a negative value along this axis right here. Does that make sense? Okay. What is the reference angle in the corner here? What's the remaining bit? If this is 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, the last little bit, 1/4, makes it 8/4. So this is pi over 4. Well, the reason why that's useful is that as soon as I know that this angle is pi over 4, that's 45 degrees, I know the other angle down here in the corner is also pi over 4. And what we can do is we can plot one of those two triangles I just showed you. The way that works then is for those 45-degree triangles, this number right here is 1. Let's write it on the other side of the negative side, though. That makes more sense. This side right here is 1. This side right here is 1. And this side right here is root 2. So now I actually have some values to plot. So then the way sine works is sine is just the y value divided by the radius if the radius isn't 1. Is the radius equal to 1 right now? Okay, so one thing I can do to fix it is I can divide everything by root 2. I can divide this guy by root 2. I can divide this guy by root 2. So the sine is actually equal to the y value, and then the y value on a unit circle is -1 divided by root 2. That is an exact value. Go back to your calculator now. You know how just a second ago I typed in sine of 7 pi over 4 and got this stupid dumb number here? Well, if you typed in -1 divided by root 2, it better be that exact same number. Does that make sense? Let's try another one then. Let's try tan of -pi over 3. By the way, trigonometry is really a bunch of really little skills that you have to put together. Like, it's all of these things we've kind of talked about at various points over either the last day and a half or last year when I taught you, or maybe even things you learned back in junior high. That's one of the reasons why I said yesterday I don't like the way we teach trig, because we do it like a little bit at a time. Sometimes I feel like it'd be better just to do it all at once. But I don't know, maybe you disagree with that. Where is negative pi over 3 going to be located? Yeah, it's actually also in the fourth quadrant. You could go forward around the circle, or this one right here says you're going backwards around the circle. I got to break things up into thirds. So this could be like 1/3. That would be 2/3. This would be 3/3 right here. So going backwards like this, that's where negative pi over 3 is going to be. We're going backwards pi over 3. Well, pi over 3 is actually 60 degrees. I'm just going to write that next to it. Which means this guy right here is pi over 6, which is 30 degrees. Well, this is a triangle that I just showed you as well. We just have to label the sides correctly. One of the sides is 1, one of the sides is 2, and one of the sides is root 3. The hypotenuse is 2. The way I try to remember it is that the 30 and the root 3 do not go across from each other. That's my way of remembering it. So I remember that the hypotenuse is always 2. I'm usually good at remembering that. And then I just know that the 30 is not across from the 3, so it's across from the 1 then. Which means that by default, the root 3 must be across from the 60. But you need your own way of memorizing this. So the 30 does not go across from the root 3, so the root 3 better be right here. The 2 is the hypotenuse, and that better be the 1 then. That's actually not right, though. I made a mistake. Good catch. Well done. Yeah, that should be negative root 3. Now, you know how last time I made this a unit circle just because? You don't have to. It'll work out the same way. Like, I could divide everything by 2 if I wanted to. Or, in this example here, tan is supposed to be equivalent to like either opposite or adjacent or y over x. So let's just put y over x. Let's make it minus root 3 divided by 1. That'll work. If you did want to make it a unit circle, by the way, you'd divide everything by 2. And what would end up happening is you'd get minus root 3 over 2 divided by 1 over 2. And then wouldn't those over 2's just cancel anyways? So you don't have to make something a unit circle, but you can if it's helpful. So let's check our work. I'm going to type in my calculator the tan of negative pi over 3. It's going to give me some really stupid number. And if I've done this correctly, it should be the same thing as negative root 3. I'm not going to divide by 1 because that's redundant. Ta-da, they're the same.
So what would you put like after it? Would you just put negative, or would you put negative 1.7?
Like, call it this one here. Don't write it 1.7. The whole point of this is to get an exact ratio, as opposed to like rounding it to like some sort of numbers. Because at this point here, this is an irrational number. You'll never be able to round this properly. Something is going to be slightly off when you round. Still okay? Anyway. Why don't I skip ahead? Let's do that diploma question that's sitting there. I feel like you guys got a bit of the hang of this. So let's try to find the exact value of this guy. Negative 3, then we times by the tan of 13 pi over 6. Now, I guess on this diploma question, you know what you could do actually? You could type this in your graphing calculator, get a decimal number for it. Type all 3 of these in your calculators, get a decimal number for all of them, and just see which one is the same as each other. That'll work. On a diploma, I'd suggest that, but just to enhance your learning, let's not do that. Let's try to solve it the way we just did. So, where the heck does 13 pi over 6 go? Well, I'm going to start counting out sixths. Here's 1/6, 2/6, 3/6, 4/6, 5/6, 6/6, 7/6, 8/6, 9/6, 10/6, 11/6, 12/6 is back to start. So 13/6 is all the way around the circle and is back in quadrant 1 again. That's where 13/6 lies. What's the little angle in the corner then? What's the reference angle then? If we went all the way around the circle, 1 extra sixth. Yeah, pi over 6. 1/6 of pi. That means this guy in the corner is pi over 3. Well, you should be able to recognize then that this is one of those special triangles that we just talked about. So you just have to make sure you can have your numbers in the right spot. The hypotenuse is always 2. Which one goes where again? That's a 30 degrees. 30 degrees is the one right here, I believe. And that's the root 3. Did I do that right?
Yep.
It's been a while. I haven't trained my brain for this a while. You need to find your own way of memorizing this, or at least write it down at first. Do I have to make any of those negative?
One.
Well, no, the one's going up actually, not down.
Oh, never mind.
That makes sense. So actually, we're good on this one. So then I'm just going to focus on this little bit right here. Tan of 13 pi over 6 is equal to whatever the opposite divided by the adjacent is. So your opposite is 1. Your adjacent is root 3. Okay, so what that means then is taking this down here, it's negative 3 times by 1 over root 3. Which, in a way, I guess you could call that negative 3 over root 3. And that's not one of the answers. Okay, you need another skill to solve this one algebraically. It's called rationalizing a denominator. We learned it last year. General convention in math is that you don't like square roots in the bottom of fractions. And so in order to get the square root off the bottom of a fraction, what you do is you times by root 3 over root 3. Do you recall this at all? The basic idea behind it is that if you times by root 3 over root 3, on the top of the fraction you'll have minus 3 root 3. But on the bottom of the fraction, root 3 times root 3 is just 3. Right? Root 3 times root 3, the roots can go away and it's just 3. And then you can cancel because there's a 3 on the top and on the bottom. So our final answer is...
What's negative 1 to 5?
So I just leave the negative on top there. That's all. I can check my work. To be honest, if this was your diploma, I would not do what I just did there. That's a waste of your time. Right? But I want to show you because I think the skills are useful in other scenarios. But I mean, the best thing to do would be to go negative 3, 10, 13 pi over 6. You're going to get a number here. And that actually happens to be negative root 3 because I just did that apparently the previous line. That'd be way faster, I guess. Okay, last bit, then I'm calling it a day. I'm just trying to think of which one we should do. Okay, let's do the other multiple choice question here. I think I can answer the stuff I would have skipped in the slide before if I just do just this question here. I mentioned to you guys yesterday the idea behind a general solution, did I?
Yeah.
Did I use that term? A general solution is where you do this whole like add or subtract pi kind of concept. The reason being is that you can always go around the circle another time. That make sense? Like let's say the answer was 30 degrees and I was plotting out a circle and 30 degrees is right here. That's an answer. Or you could have gone backwards around the circle negative 330 degrees. Or you could go all the way around the circle 390 degrees. And all of those are valid answers. So what we do is we write a general solution referring to all of the possibilities. Okay. I want to talk about that in answering this last diploma question. Then. So we want to try to solve this guy. In order to solve this, hopefully you notice right away that there's a root 3 and a 2. Doesn't that kind of ring some bells? And you're going, whoa, 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 hang on, we just talked about that? That's that 30, 60, 90 triangle. So I might suggest let's divide both sides by 2. So then we can get it to the point where sine of theta equals root 3 over 2. Okay, now let's plot a graph. Where is sine of theta a positive value? Here? No.
No, this quadrant.
Here? Yes. Can happen here. Here?
Yeah.
Yep. And in the last quadrant, no. Now I'm going to plot in some more stuff. So it appears that my opposite, which is my y value, is root 3. And that my hypotenuse or radius is 2. What's the other side of the triangle going to have to be by default then? 1 and negative 1. Good catch, Brad. Because in that quadrant there, it has to be negative. It's a lot of little things, hey? Like, all of these skills that I'm working on today, I feel like you possess them. We've worked on them. You have to be able to put all of them together. What angle goes in the court? This is 60 degrees, yep. And that makes that 60 degrees. Now, all of these, though, are in radians, not in degrees. So 60 degrees is actually equal to pi over 3. If this guy right here is 60 degrees, then he's also equal to pi over 3. But I actually need to find the angle going all the way around to there. Because this is actually the reference angle here is pi over 3. Anyone have any ideas how to figure out the whole angle all the way to there?
180 take away 120.
Well, that'll work. It's actually 180 take away 60 and it equals 120. Maybe here's another way of looking at it. Here's your first third of pi. Here's your second third of pi. Here's your third third of pi. So this angle right here is actually 2/3 of pi. This is 3/3 of pi. Minusing 1/3 of pi means the rest is 2/3 of pi. That being said, are those the only two answers that work? Well, you could go around the circle more than once. For example, you could go all the way around the circle once and then show up there. What did I do? Well, I took my 1/3 of pi and I added 2 pi. Now, could I go backwards around the circle? Sure. So I could subtract 2 pi. Could I go around the circle more than once? So that means that we throw like an end there, implying that we don't know how many times we're going around the circle. And really, that same logic applies to this one right here. You have an answer of 2/3 of pi, but you could go around the circle an unlimited number of times, and you'd end up in the same spot. These are known as general solutions. So our answer is D. They're backwards, obviously, but... I think that's as good a spot as any to stop. Okay, so quick summary and then we'll be done for the day. A lot of these skills, I really hope, especially like this plotting stuff on a unit circle, I try to do a lot of it in grade 11, knowing that trig is sometimes a hard unit in grade 12. So I hope you guys are fairly comfortable with the idea of, here's that grid, plot a point on the circle somewhere. I hope you're also fairly comfortable knowing what sine and cosine and tan are, and their opposites. You might just need to write them down at first, but you'll get better at those. The trick now is, can you do this in radians? Because that's a different mind-blowing way of trying to write down angles. You may need to use reference angles to figure things out. You may need to use that cast rule to go CAST and figure out where things are positive and negative. Typically, there's more than one location that things can be in. So you have to have good critical reasoning skills. When you get an answer from your calculator, don't assume that that is just the answer, because your calculator might have found some other answer as well. Last thought is there's these two special triangles you should know about. One of them is a 1, 1, and a root 2. That involves 45 degrees. The other one is 1, 2, and root 3, and that one involves 30s and 60s. And you should be familiar with those. That's more or less my lesson. That one you should know, but we don't actually work with the angles inside it. But you should hopefully recognize it and go, hey, look, there's a 3, 4. You can just say, no, it's 5. Okay, any questions? Thank you for bearing with me for a really long time. Sorry. Thank you for being here for an hour and 5.